Right, welcome everyone to our final HESE colloquium talks today. Today's speaker is Dr. Brandon Murphy. He's a professor of geology at St. Francis Xavier University, Nova Scotia. He has Bachelor of Science Geology from University College Dublin, Master of Science from Acadia University, and PhD from McGill University. His research focuses on supercontinent and global scale orogenic processes related to the cyclic amalgamation and breakup of supercontinents and their relationship to the evolution of the Earth. Professor Murphy has published more than 330 research papers. He has won national and international award for research, service, and outreach, including the prestigious Killam Research Fellowship, Fulbright Scholarship, and he's a fellow of the Royal Society of Canada and the Geological Society of America. So, Dr. Murphy, you can start your presentation.
Okay, thank you very much, Mustafa, for the kind introduction. My wife would recognize that introduction at all, but thank you all for showing up on Zoom. You must all be zoomed out by now. So I do appreciate you attending virtually. My key message here is that, especially for emerging geoscientists, is that we are on the cusp of a really exciting time in geosciences where geodynamic models and geological constraints can be married pretty near for the first time to provide us with new insights into coupling between the lithosphere and the convecting mantle beneath the lithosphere. And I'm going to use the controversy about Pannotia as an example. I'm not going to offer any robust solutions to the controversy. Instead, it's more or less signposts. I'm going to show you the importance of the controversy, give maybe an approach to solving the controversy, and I think you'll see potential in this approach. So, Pannotia, as you see in that, that's one version of it. It is a hypothetical, hypothesized supercontinent that some people, not everyone by any means, think came together in late Neoproterozoic. And the key component of it is Pan-African orogenesis that you see in the sort of interior origin color there, sort of pale, well, sort of an intermediate shade brown color. You can see it, and that's those interior origins, what you see there, are really the relics of ancient tracts of oceanic lithosphere that brought in the surrounding continents of Gondwana together. And there's evidence that it affected the chemistry of the oceans and the atmosphere at the time. And that this was the time of the snowball, the last of the snowball glaciations. And those of you who work in this field know that it's also a time of great biological innovation as well. It's a crucial interval of Earth's evolution, and the fundamental template of it, the existence or not of a supercontinent, is what is really fundamentally controversial. So what I'm going to talk about is actually, it's the product of two papers that are now in press. You see them there up in the upper right. And so I'd like to thank this sort of soccer team of co-authors here, and to many IGCP participants over the years who have really helped stimulate a lot of this thinking. So what I'm going to first do is give you a review of what we think we know about the supercontinent cycle. Then I'm going to zoom in on one hypothesized supercontinent, Pannotia. Why do we have problems, and why? And what is the evidence in favor of it? But then I'm going to step back and say, actually, this is a bit of a sideshow. What really is important is not so much whether Pannotia existed or not. It's whether it really fundamentally disturbed mantle circulation patterns. Because if it did, this is something we have to factor into models about the origin of Pangea, the supercontinent we think we know something about. But when you think about it, it's rather embarrassing when you think about it, is that we know to a first order where and when Pangea formed. But we don't really have a handle on how and why it forms, the actual mechanisms involved. despite the fact it's one of the first things we all learn in geology, we really don't know how Pangea formed. And then the last part of the talk, I'm going to point about the way forward. No solutions, but signposts. So, what do you think we know about the supercontinent cycle? Well, the first paper to mention the word supercontinent cycle was Damien Nansedal, 1988. And he's essentially, it was the principle that the Earth tectonic evolution has essentially been doing laps of the track, you see in the bottom right there, that the supercontinent amalgamate, it breaks up into these interior oceans, break up, flanked by passive margins, and then subduction starts to bring the supercontinent back into configuration again. So we go 1, 2, 3, 4, and we basically do laps of the track. And so you see in the upper right, you see as you go backwards through time, Pangea gives way to Pannotia, and then backwards to Rodinia, and back through time to Columbia, that people think amalgamated about 1600 million years ago. So if you look above that, you'll see a little brown bar of continental collisions. These are the collisions that bring the supercontinent together. So n equals 5 would be the Pangea collisions, n equals 6 would be the Pannotia collisions. They're effectively Gondwana, etc. So according to the supercontinent cycle, the Earth's evolution is punctuated by episodic and assembly of supercontinents. And there are several. Pangea is just the most recent of those supercontinents. As we'll see, there's a lot of evidence that profoundly influenced the Earth's systems, not just the lithosphere. Of course, it would likely affect the rock record more than any other phenomenon, but it also would have affected climate, biogeochemical cycles, the biosphere, the hydrosphere, and the atmosphere. And as we now can track subduction zones all the way down to the core mantle boundary, almost certainly tectonics, there's a feedback between lithospheric tectonics and what goes on within the Earth's interior. I can skip that one. So, Pannotia, again, what are we talking about here? We're talking about the amalgamation of Gondwana, but at the time that Gondwana amalgamated, the South American portion of it was amalgamated to Laurentia and Baltica, and depending on who you believe, plus or minus Siberia. And one of the key tenets of it is that those Pan-African collisions that you see that bring Gondwana together must have occurred prior to the separation of Laurentia from South America. In other words, you can't get divorced before you get married. You can't split up before you get together. And that's a major debate. So as we go back through time, it's really important to realize that all these supercontinents are works in progress. Configurations are being debated and refined all the time. So this is two different views of the configuration of Rodinia, the billion-year supercontinent. Here's some different views of Columbia. Some people call it Nuna. Again, the configurations may differ through, from one set of authors to another, and they're still works in progress. But the past is the key to the future. So we all know that over the last 200 million years, the Earth's evolution is profoundly affected by the breakup of Pangea and the opening of the Atlantic Ocean. And the past, as I say, is the key to the future. And thanks to GPS technology now, we know we can measure the rate at which the plate's moving and the direction in which they're moving. And so you can see, you can extrapolate the future geography of the Earth. So as we go into the future, using these GPS measurements, you can see that the Atlantic is going to expand at the expense of the Pacific. You can see Australia finally gets its wish and enters the Northern Hemisphere. And you can see the Pacific Ocean contracting. And in 75 million years from now, if the plates keep moving in the direction they are now, that's a big if, but if they do, then we'll have another supercontinent called Pangaea, if we've already got a name. And our neighbors to our west will be the east coast of Australia. So if you actually look at the configurations of the supercontinents over time, Pangea, upper left going to the putative Pannotia, then bottom left would be Rodinia, then onto Columbia. The actual configurations have changed from one supercontinent to the other. And so the way it was originally envisaged, Damien's original cartoon to the upper right, he would agree that is oversimplified, and we need to talk about n-member possibilities of forming supercontinents. So the cartoon on the left is supposed to depict that. So we form supercontinent A and break up to form new interior oceans with flanked by passive margins. So we can go from A to B to C. There are two n-member ways, and I stress n-member ways, by which the next supercontinent can get together. The interior oceans that you see in yellow may subduct as envisaged on the cartoon on the right, and we go A, B, C, D, in which case we end up with a supercontinent with similar configuration to the previous one, something we would call introversion, preferential subduction of the interior oceans. Or another end member is, as we just saw in the cartoon projecting us into the future, an expansion of the interior oceans like the Atlantic, contraction of the exterior oceans like the Pacific, and we go A, B, C, but then to E, to give us a supercontinent that actually turned inside out, extroversion. And this is what Pangea is projected to be in the future. But there is a third n-member model, so it's a ternary, if you like. And this one is a really elegant model because it takes into account the Earth's connection between the lithosphere and mantle convection. So if we look at the modern Earth, it's dominated by P and A, two quasi-stationary antipodal upwelling zones. And what they actually reflect are identified by seismically by their large, low, shear velocity provinces. It's debated whether they have long-term stability, certainly since the breakup of Pangea. Some people think they're actually fixed through time. Other people think, and we're going to debate this a little later, that they actually are, there's a feedback between them and the supercontinent cycle. So the two quasi-stationary upwellings, P for the Pacific, A for the Atlantic, and their equatorial locations reflect the optimal moment of inertia on a spinning Earth, and they're bisected by a girdle of downwelling, that's north-south girdle of downwelling. Intriguingly, and this is important, I know a lot of you are interested in mineral deposits and the like, that large igneous provinces and hotspots, intriguingly, are positioned, almost all of them, are positioned along the edges of these upwelling zones. And that will be important later on as well. So, what is this other model for forming supercontinents that uses this context? Here we go. So the mantle geodynamicists will tell us that the supercontinent aggregates over a mantle downwelling. If you see B there, I don't know what happened to A, but anyway, if you see B, up at the top, you'll see a gray cap, and that gray cap is sitting above this blue zone. The blue is cold, it's the downwelling. These are actually subduction zones extending down to the core mantle boundary and draping the core mantle boundary. And what they reflect then is the hauling in of dispersed continental fragments into that zone. Then, as we go from B to C, there's a whole bunch of processes that combine to turn that downwelling into an upwelling. We're going to go through them a little bit later, but there's a whole bunch of processes, the relative merits of which are aggressively debated in the literature. But the net effect is the downwelling becomes an upwelling. And you can look on the right here, you can see the effect of that. If you look at a reconstruction of Pangea over there on the extreme right, you can see that Pangea, which would have obviously formed together on a mantle downwelling zone to bring all the continents together. You can see if you look at the African LSVP at the moment, the A LSVP, it sits underneath Pangea. So that downwelling converted into an upwelling. So then we have two upwelling zones as we go on to the left-hand cartoon again, bisected by that girdle of downwelling. So according to this third end member of how you can get a supercontinent in the future, you can see on the left-hand side the two antipodal upwellings in yellow, the yellow fingers, the subduction girdle downwelling is in green. And then if you look on the right-hand side, you see the two upwellings again on either side, and there's the downwelling in the center, the girdle of downwelling. And so what is projected is the continents migrate to this girdle and then they move along the girdle. And more about that a little bit later. In which case, the next supercontinent will not be formed by closing the Atlantic, nor will it be formed by closing the Pacific, but the future Pangaea will be formed by closing the Arctic Ocean and bits of the Southern Ocean. This is the principle of orthoversion. If you look at the bottom there, the continental fragments gather as a new supercontinent assembles 90 degrees angle away from the predecessor. So the three end members, and you'll see that all three are going to come into play a little bit later on. Okay, specifically, what is it about Pannotia that gives us problems, and what's evidence in favor of it? So, as you might imagine, like all global reconstructions, there are debates among different authors about what the configuration is. Now, all these authors agree that there is a supercontinent, but they disagree on where the bits lie, the various continental fragments lie. Fair enough. But if you look at this set of reconstructions, most neatly by Meredith, and these are plate reconstructions, you can see plate boundaries in there, they're not just continental reconstructions. You can see that, and it's in 2017, you can see that by the time we get to 520, the gray shaded area, Gondwana, becomes packed. But before it gets fully packed, Laurentia, L, and Baltica, BA, over in the center and on the extreme right, they've already separated before Gondwana fully assembles. So you can see no sign of Pannotia in this set of continental configurations. So why are we having this problem? Older supercontinents like Rodinia, we agree on through a first order that they exist. Why are we having this problem with Pannotia? First, it's because of the paleomagnetic record. In the Ediacaran, there are problems in understanding that record because of evidence of intervals of true polar wander, and because of evidence that the Earth's dipole field, the modern field, may not be equivalent to what existed in the late, in the Ediacaran. There may be something else going on. There was distortions in the field. So that even people who work in paleomagnetism recognize that the record is ambiguous. Secondly, and you saw the influence of that in those previous reconstructions, as we've got more precise ages of the Gondwanan collisions, some of them are clearly younger than the onset of rifting of Laurentia away from Amazonia, Laurentia and Baltica away from Amazonia. The other aspect of this is size. Was Pannotia ever big enough to merit the status of a supercontinent? And you might say, well, size, that's just an accounting process. And to some extent it is. But the key thing that we'll discuss a little bit later is that the continental landmass has to be a sufficient size to influence the mantle circulating beneath it. So size might be a significant factor. But one thing is for sure, that even those who promote the existence of Pannotia will agree that if it existed, its existence was fleeting, much less than the tenure of Pangea, much less than the tenure of Rodinia. Okay. Our point is we feel that Pannotia, whether it be existed or not, may be actually distracting us as we're debating whether it exists or not, may be distracting us from a much bigger issue. And that issue is, did those Pan-African orogenies, did they impart a legacy in the mantle that must be factored in to models that form Pangea? Let me give you an example of potential significance of this to the origin of Pangea. Let's first look at a model that ignores Pannotia, says that Pannotia is not, or Gondwana amalgamation does not affect the supercontinent cycle. So in this view, Rodinia to Pangea is one supercontinent cycle. So if you start at the bottom and work upwards, you'll see the Rodinia about to break up at 750. It forms these internal oceans that you see in yellow. So that's the equivalent of B in the cartoon on the right-hand side, expanding to C. And what the internal oceans keep expanding. So it's like the modern Atlantic expanding at the expense of the exterior oceans, the external oceans. So it'd be, in the modern example, would be the Pacific. Till eventually we form Pangea by essentially turning Rodinia inside out. This would be an example of Rodinia to Pangea by extroversion, by preferential subduction of that blue ocean, replace it by the yellow ocean. And this then implies that Gondwana had no thermal legacy, had nothing to contribute to the origin of Pangea. On the other hand, if you hold that Pannotia is a supercontinent, then, as many of you know who work in the Appalachians know, that what eventually happened is as Laurentia and Baltica separated from Gondwanan portion of Pannotia, we opened up the Iapetus Ocean and we opened up its successor, the Rheic Ocean. But those are exactly the same oceans that preferentially subducted to give us Pangea. So in our cartoon on the bottom left, we go from A to B to C, and we subduct those very same oceans to give us the next supercontinent. In other words, go A, B, C, D. So our motivation in understanding the geodynamic significance of Pannotia is actually trying to understand how Pangea formed. What is Pannosia's thermal legacy to the Paleozoic? And as I said, I'm not going to give you any solutions because I think it's going to take a generation to solve. I'm going to maybe put some signposts down. And many of us have worked on these international geological correlation projects. And these are sort of ideal projects to do a global scale sort of analysis like this. That involve lots of targeted work and lots of field work in targeted areas, lots of analyses needed, as I'll give you some examples of in a few minutes. So, was there a disturbance of the mantle in the late Neoproterozoic during the Ediacaran? Well, there are a lot of proxies that we can use. There's a list of them there. You don't need to worry about now. I'm going to go through them in turn about the significance of the Pan-African origins in terms of changing and influencing the mantle beneath it. Typically, supercontinents will mark the end of one cycle. You complete one lap of the track and you start and you outgo on the next lap. And so what we need to look at is that recognition can be taken beyond paleomagnetic reconstructions, and we look at a wide range of these proxies because we don't have the paleomagnetic record to help us. So first, to reiterate what we said already, clearly, if you're going to have a supercontinent, you need global scale orogenesis. And for assembling the Gondwanan portion of Pannotia, these are the Pan-African origins. And they're certainly one of the largest orogenic systems that we've had in Earth history. Not just what you see in the dark shades that brought Gondwana together, but as those subduction zones got expunged between the converging blocks, they migrated to the margins of those blocks. We got subduction around Gondwana as well. So, as those mountain belts formed, uplifted and eroded, you'd expect the sediments shed from them to be dispersed in many different locations. So you'd expect if there was a lot of magmatism of continental arcs as the blocks were coming together, and then granitoid magmatism as they collided, you'd expect that to be recorded in peaks in detrital zircon and monazite ages. And now there's databases, the one I'm showing you there is 100,000 database. There's now a lot more than that, but essentially they're sort of the same thing. And they show not just peak in zircon populations in the late Neoproterozoic, you see in the red bar for Pannotia. You also see lots of evidence of enhanced metamorphism associated with that collision. Granulite facies metamorphism, eclogites, high pressure metamorphism, evidence of deep subduction associated with these collisions. All hallmarks of the Ediacaran telling us there's something, deep subduction telling us something that's going into and influencing the mantle. Other proxies, I'm going to go through them relatively quickly. Other proxies would include a lot of evidence for crustal recycling. One of the proxies for that is looking at the hafnium isotopes in zircons, which take on a negative excursion there. You can see it dips down pretty low. Whereas the high elevated values in oxygen isotopes, again in zircons, tells you that the magmatism was accompanied by a lot of reworking of sedimentary material. And you can see that it's true of most of the times of supercontinent assembly in the past, those little gray bands, and Pannotia has exactly the same signature. But there's other proxies as well. There's sea level. Pangea is a good example of a supercontinent that corresponds to periods of very low global sea level, mainly because supercontinents are uplifted. As we've talked about, the downwellings turns into upwellings. There's a continental insulation that's trapping mantle heat. So for example, if you put on an electric blanket on your bed and you leave a book on that electric blanket and you leave it there for long enough, for 5–10 minutes, and you come back into the room, the heat builds up at the base of the book on the electric blanket. It's blocking the escape of the heat. Similarly, continents are insulators on top of the mantle and they trap mantle heat, and essentially they warm up and they undergo uplift as a consequence. So Pangea is an example of low sea level as a consequence, and you can see Pannotia has got exactly the same signature. Climate. Well, supercontinent assembly results in deterioration of the climate because of the drawdown of CO2, atmospheric CO2. That's because you have all these brand new mountain belts that are undergoing weathering, and weathering draws CO2 down from the atmosphere. And so the Ediacaran has exactly the same sort of signature as Pangea does. And in fact, in the Ediacaran, we're dealing with the last of the snowball glaciations and major intervals of glaciation. And as we know, Wegener used the glacial deposits in Pangea to help him reconstruct what Pangea looked like. There's also the effect on the biosphere. Amalgamation, I mean, mass extinctions are obviously very controversial, and so the mechanisms here are not as important as the signals. You can see that Pangea corresponds with the mass extinction. Some people think, not everyone by any means, that it's a result of the loss of shallow marine habitat, and there's obviously certainly other contributors as well. But the most important thing is Pannotia has the same sort of signal, the loss of diversity. And in the late Ediacaran, there's a decline in stromatolites and extinctions among acritarts and palmiflora. What about breakup? Well, breakup, the heralding the breakup is a lot of continental rifting events. And here we're looking for mafic dike swarms and large igneous provinces, which may well be the surface expression of plumes. Well, we know, very well documented, the central Iapetus magmatic province, widespread rifting and magmatism associated with the breakup of separation of Laurentia and Baltica from Gondwana, and different manifestations of that. So there is obvious evidence for breakup. And that corresponds with sea level change. So just as a supercontinent, as it amalgamates, gives us low sea level, the breakup of a supercontinent results in marine transgressions, results in sea level rise, major sea level rise. And there's several contributing factors to it. First of all, obviously we have passive margins develop as the continents separate, but the continents themselves subside as they move away from the upwelling zones. But also, if you consider a ocean basin to be like a bathtub full of water, and you put a large object in it. So if you're about to get into a bath and it's full of water and you sit in the bath, obviously it displaces the water upwards and outwards. Well, similarly, if you put a new mid-ocean ridge, which is essentially a submarine mountain chain, into an ocean basin, it's going to displace water upwards and outwards, and you have a rise in sea level. It happened for the breakup of Pangea, and we've got development of the rise in sea level and passive margin development for the breakup of Pannotia as well. The climate recovers. We have it for Pangea, we have it for Pannotia. The breakup coincides with warming because of the buildup of atmospheric CO2, and that's because of decrease in continental weathering. As sea level rises and floods the continents, clearly the continents are going to weather less. Also, there's a lot more magmatism and exhaling of CO2 out of the new mid-ocean ridges. So just as the Mesozoic was a period of a greenhouse climate, so was the early Paleozoic following Pannotia breakup. And then there's evolutionary radiation as a consequence. Well, again, this would be open to debate as what's causing this, but the most important thing is that the same pattern after Pangea breakup, Pannotia follows that same pattern. And of course, the Cambrian explosion is embedded in that breakup signal for Pannotia. There's a lot of geochemical proxies. I just mentioned one of them here, and that is, you can see in the blue curve, the abrupt rise in strontium 87-86 ratio, which reflects erosional release to the oceans from the continents of radiogenic strontium. So this is sort of an index, if you like, of the contribution of continents to the marine seawater record. And so you can see that rise in the aftermath of the formation of Pannotia, sorry. Also, another proxy is steep rise in atmospheric oxygen levels. In fact, for each supercontinent, according to Campbell and Allen, each supercontinent assembly, there's a little step increase in oxygen levels. And this is interpreted by them, although this is open to debate as to what's actually causing it, enhanced marine productivity resulting from an increase of the erosional release of nutrients. But you can see that stepwise increase in oxygen level in Pannotia in that red band there as well. So that's a review of the proxies that tell us something profound is happening in the late Neoproterozoic. And so going from Rodinia to Pangea and treating it as one supercontinent cycle without a disturbance in the middle may be a little simplistic. So for us, the main issue is whether Gondwana, the amalgamation of the Gondwanan portion of Pannotia, imparted a thermal legacy in a mantle that must be factored into models that form Pangea. In other words, we can't go from Rodinia to Pangea as one cycle and ignore this effect. So if indeed there is a mantle legacy and a thermal legacy, how would we recognize it? So I'm going to go through two ways of which we might be able to, again, these are signposts, we might be able to recognize this in the future. The first way is the prediction of where plumes should impact on the lithosphere. And the second is to introduce a concept of megacontinents, which is currently in this article in press. Okay, so let's talk about what we know about mantle convection and how it fits in. Today, again, we've got two quasi-stationary antipodal upwellings that straddle the equator. They're bisected by a north-south girdle of downwelling. And there are large igneous provinces and hotspots distributed along the margins of these upwelling zones. There's a debate among the geodynamicists about whether these, the African and the Pacific superplume are actually fixed, or whether they change in time in response to the supercontinent cycle. So I'm not going to call these models, I'm going to call them scenarios. Let's take the example of these LSVPs being fixed. So that's pretty easy. Then what we can do is we can put them on these various reconstructions and test it against the geological record. So right at the outset, I said, we're at the cusp of being able to marry geology with geodynamics. Here's a potential way of doing it. So you can see what this scenario predicts. If the LSVPs are fixed, you can see one of them is underneath Laurentia. So if they're quasi-stationary since the Neoproterozoic, then the Laurentia should have been influenced by one of these LSVPs. Let's go to scenario B. Now this diagram comes straight out of Robert's paper in 2018. So this is exactly as they portray it. And what it's looking at here is Laurentia in a fixed mantle reference frame. And they're looking at type 2 convection. So in yellows are the upwellings, and in red are the downwelling girdles. And what you can see in this mantle reference frame, that Laurentia also sits on top of one of those upwellings. So let's look at the geological record and see, is that supported? Well, we certainly know in the late Neoproterozoic, we've got the central Iapetus magmatic province on the eastern flank of Laurentia that is held to be responsible for the separation of Laurentia, Amazonia, and Baltica. But what about the rest of Laurentia, the external margins of Laurentia? So if you look at the tectonic stratigraphy of the rest of Laurentia, you see it's completely dominated by siliciclastics, and mafic rocks are very, very scarce indeed. For those of you who know about the gun barrel or the Franklin dike swarms, they're too old. They're 780 and 720. They're too old to be part of this Pannotia Gondwana story. Here's another example of stratigraphic sections. This is from Idaho. And again, just you can show many, but basically mafic magmatism that would be attending or would be an expression of plume magmatism just is very, very minor indeed. So let's look at the third scenario then. And this is where there's a feedback between the supercontinent cycle and mantle convection. So as we discussed, if you look at the left, a supercontinent is going to assemble above a mantle downwelling. These reflect the subduction zones that are going to drape the core mantle boundary. So this is what we call on the left during the assembly, we call that type 1 or degree 1 mantle structure. And we call it degree 1 because it has one upwelling and one downwelling. But then that mantle downwelling evolves to become an upwelling. So now we have two upwelling zones, two antipodal upwelling zones, bisected by this subduction girdle. Two upwelling zones, we call that degree 2 mantle structure. And so the supercontinent cycle, if you like, is attending a fundamental change in mantle structure from degree 1 to degree 2, from one upwelling to two upwellings, from a centralized local downwelling to a girdle of downwelling that we see today, where the subduction girdle will bisect the two antipodal upwellings. So this is a geodynamic model from Tanadal, and that blue at the bottom is one of those subduction graveyards that's on the core mantle boundary. And what you see, let me just go back here, what you see in these upwellings are these plumes that are coming from the edges of the subduction graveyard, just as you saw in, how many samples back here? Just what you see in that slide. You can see around those zones of upwellings, you see preferentially the large igneous provinces and the hotspots. So that is, sorry for going back and forth like this, that is essentially what you're seeing in this geodynamic model. Now, what I did is I took this model and I cheated. What I've done is you see Gondwana situated over the subduction graveyard, because that's where the convergence was, the Pan-African orogenies. But Laurentia has no internal orogenies at all at that stage. So the plumes that come in this model, you can see, are actually going to affect the margins of Laurentia and Gondwana, but are not going to affect the external margins of Laurentia. They're not going to affect the external margins of Baltica either. So let's have a look at the geological record and see, does that match? And we'd go to the Meredith reconstructions, and Meredith is a non-Pannotia reconstruction. And so what you see in the red dots here, this is, I hasten to say, clarify, this is just a literature survey. So you go through literature and you look at individual local studies that independently assign their magmatism to plumes. And I think what you see, particularly at 520, is a really impressive match between the locations of possible plume magmatism and the Gondwanan portion of Pannotia. Now, some of these literature survey, some of these papers are 10, 15 years old, and we have more sophisticated ways of trying to identify plume magmatism. But as I say, this is just a signpost. Now, this will involve a global effort to try and document and see if this is possible. At least the signpost, the prerequisites are favorable. And what you'll see is that there is no sign of plume magmatism on the exterior margins of either Laurentia or Baltica, telling us that this disturbance was around the Gondwanan margin. And if this is right, I know a lot of you are interested in mineral deposits. This has got to have significant implications for mineral deposits and endowments of metals around the margins of Gondwana, for example. So here's the same data plotted on a different Pannotia reconstruction, this by Ian DL. And actually, it doesn't really matter whose reconstruction you use. You've got a striking coincidence of plume-related magmatism, at least as reported from the literature, with the Gondwanan margin, but not either Laurentia or Baltica or Siberia for that matter. Okay, so let's see where we are. We're talking about the geodynamic significance, even if you don't think Pannotia existed, the very amalgamation of the Gondwanan portion of Pannotia, there is a lot of evidence that there is a thermal disturbance in the mantle. So whether Pannotia is or not a supercontinent, it looks as though there's some thermal legacy that goes on into the Paleozoic that may have to be factored in to model the form Pangea. As I say, this is just a signpost. It'll take a generation to solve probably. And I think those of you who've experienced IGCP projects will probably readily agree that they're ideal for tackling projects like this. It will involve a lot of field work in targeted areas, a lot of strategically selected samples. It's got to have implications for endowment of metals as well. But very importantly, as we move forward in this, the benefit of continuous feedback between the geological and geodynamic communities is really important as both fields progress. Okay, the way forward. We have evidence that there is this thermal disturbance around the margins of the Gondwanan portion of Pannotia. But the Gondwanan portion of Pannotia is only 50% of the size of Pangea. So does something of that size, limited size, is it going to affect global patterns? So, and this is mainly from the Wang et al. Paper, and if you get a chance to download it, it should be up online now. This is the concept of megacontinents. And it turns out that Gondwana, as you see on the upper left, is clearly a subset of future Pangea. In today's world, modern Eurasia, India has already collided with Asia, may be a subset. In other words, there's always been collision since the breakup of Pangea, but this is a subset of future Amasia. Similarly, in the past, although the names might be more controversial, Nuna, as you see on the left there, is essentially Laurentia, Siberia, and Baltica, is a subset of future Colombia, which brings in Australia and whatever was connected to it. Similarly, Umcondia, you can see Amazonia, West Africa, and the like, is a megacontinent relative to Rodinia, which formed when Laurentia and whatever was attached to Laurentia came in and collided. So there's evidence in the geological record that megacontinents actually exist before supercontinents. So there's some, if you like, distortion, systemic distortion within the simple supercontinent cycle. So for example, if you want to look at an example in the Mesozoic, Cenozoic world, as we've said before, in the upper left, you can see that, that Pangea had an LSVP underneath it, this zone of upwelling underneath it, but it's our second zone of upwelling. So you see the blue there, that's the girdle that forms. What's happening on that girdle right now? Well, Eurasia has formed as India has collided, and Australia is about to move northwards along that girdle. So the Eurasian megacontinent has formed, basically. So, as has been repeatedly pointed out, the supercontinent cycle seems to be the transition from degree 1 to degree 2 types of mantle convection, where we go from one downwelling and one upwelling to 2 upwellings and a girdle. As pointed out by Conrad, there are going to be times in that interval where the harmonics of 1 and are more or less equal. And perhaps, and again, this is just a signpost, perhaps this is how megacontinents form. So consider this as a possibility. Essentially look at the down diagram here that looks like a stereo net. So what you've got is a degree 2 system with 2 antipodal upwellings straddling the equator, and you've got a girdle of downwelling. And in the left-handed cartoon, you can see the arrows are all the same length, telling you that the degree of downwelling is equal everywhere along its length. Well, that's virtually impossible because the downwelling, the rate of downwelling is the rate of subduction. And the rate of subduction depends on distance from the polar rotation. So from the Euler polar rotation. So the parts on that subduction zone system that are 90 degrees away from the Euler polar rotation have to have an enhanced degree of downwelling as the lower plate subducts. So if it's an enhanced degree of downwelling, perhaps then along the girdle, there's one area along the girdle that has a stronger downwelling than somewhere else. Maybe that's where a megacontinent forms. So if you look at the third little circle there, that's where our megacontinent forms. As the continents disperse away from, let's say, Rodinia to the girdle, there's a preliminary aggregation of a megacontinent along the girdle. But as we've seen, on that scale, on that degree 1 scale along that girdle, that downwelling locally converts into an upwelling locally along that girdle, and you get the evidence of plumes all the way around Gondwana, which basically means, therefore, that that no longer is the most intense zone of downwelling along that girdle. And instead, Gondwana would migrate. It's hemmed in on both sides by the LSVPs, by the yellows. The only place it can migrate is upwards along the girdle, where it will collide with the continents that have already got there. In this case, Laurentia, for example, and Baltica and the like. And essentially that gives us the collisions to form Pangea. Last slide. These are they're just signposts, but, and they're probably incorrect. That's not the major point. The major point I'm trying to get across is that we're really at this exciting time where for the first time we can actually try and marry events in the lithosphere with fundamental changes in mantle circulation. There's evidence of fundamental changes in mantle circulation along the margins of Gondwana. Whether it's big enough to affect global patterns, we don't know. But even if it affects local patterns, that might be enough to migrate along the girdle to form Pangea. In general, we can evaluate these geodynamic models in the context of constant amalgamation and breakup. It also may give us mechanisms for why some of these events form. Those who've worked a lot in the Appalachians have been told repeatedly that we've got the opening of the Apid Ocean beginning in the late Neoproterozoic, continuing on into the early Paleozoic, but we really don't have a mechanism for why it happened. We know when, but we don't know why. Perhaps the opening of the Apid Ocean is because of the amalgamation of Gondwana, the subduction graveyard, the plumes emanating from the sides of those graveyards. Indeed, when you think about it, it would explain why all supercontinents tend to rift apart in some locations before they fully amalgamate in other occasions. So you can actually, parts of you can get divorced before other parts of you get married. It also would explain why terrains can repeatedly fall off those margins. Those who work in the Appalachians, work in these peri-Gondwanan terrains, there's repeated spalling of terrains off the Gondwanan margin over time. And it actually continued beyond the Appalachians, the Cimmerian terrains, and arguably it's still going on throughout the entire Paleozoic. There's evidence of fundamental changes in mantle circulation beneath these megacontinents, maybe even if it is a supercontinent on a global scale. But one thing's for sure, we think, is that if you take a shortcut from Rodinia to Pangea and treat it as one supercontinent cycle, you're missing the possibility for understanding these early Paleozoic mantle circulation patterns that will help us understand how Pangea formed. And finally, the concept of a megacontinent as a precursor to formation of supercontinents, Gondwana as a precursor to Pangea, may be worth considering. Okay, well, thank you all very much.
Thank you a lot. That was a very fascinating talk. So anybody have questions, you can type in the either chat box, or we encourage usually graduate students to try to ask first questions. So if any of the students have questions, you can turn on your microphone and ask your questions.
Oh, I have a little question. I'm Xuyang.
Yeah, go ahead.
I have broader questions and not so specific to the Pannotia. For the supercontinental formation, is a subduction process necessary during the formation, particularly for 2.7 billion years superior continental formation?
Yeah, you've touched on a critical area of uncertainty here. I was at pains to sort of start everything at about 2 billion, because as you know, everything before 2 billion is very controversial as to whether the supercontinent cycle ever existed, whether it goes back that far. And those people who work on the supercontinent cycle are fairly confident for the last 2 billion years, but before 2.7 or before 2 billion, going back as far as 2.7, certainly there are other mechanisms, as you know, that may be responsible, and whether subduction is an evolution of those is yet another sort of really important but enduring debate.
Okay, yes, thank you.
So the answer to your question is, direct answer to your question, is subduction necessary 2.7 billion years ago? I'd say most people working on that would say probably not. There are other mechanisms that can do it.
Yeah, thank you.
Anybody else? So, Alessandro, you had a question. You want to ask your question?
Hi, yes. Thanks for the talk.
I like your backdrop. I like your backdrop, by the way.
Thank you. It's the Rocky Mountain Trench.
Well, pretty good.
My question is essentially similar. I was wondering if the models of introversion, extroversion, or orthoversion can be used in any way, shape, or form as templates for Superior or perhaps Nunavuttia, those supercontinents that in a way or another are postulated to have existed, but for which we don't have the magnetic records.
Yeah, I think you've got to be extremely careful going back that far, to be honest. And the reason being is that everything is operating on a much, like if you talk about the Superior, for example, and all the evidence of accretionary tectonics in between the disparate blocks bringing Superior together, they're operating on such a localized scale, you can hardly envision them affecting global mantle convection patterns. And you could also imagine, to use a rather nasty word, they can be trumped, if you like, by mantle convection patterns that happen elsewhere on the globe that happen to be stronger. So we're dealing with really fragmentary evidence when we get that back far, but I think that the thing about it is the scale is not sufficiently large to affect global scale mantle patterns.
Could Superia be considered a megacontinent? Because Superia, that we know of, includes a pretty large chunk of fragments. Like now, they're even attaching Valbara to it, right?
You know, that's a
So
brilliant
it
question.
becomes sizable.
Yeah, that's a brilliant question. And I'll pull back off that a little bit and maybe make a connection. And that is if you subscribe to Walter Bleeker's story about supercratons, for example, as you make the transition from supercratons to supercontinent, you can, as you go through this transition, you can probably see the scope of forming several megacontinents before you form that first supercontinent. So there must be some transition in there as we go through how sort of some subduction system that we would recognize as being something similar to today would have taken place towards the end of the Archean and the early Proterozoic. Yeah, great question. I mean, you're touching on, both of you have touched on critical areas of uncertainty. So there's one thing that begins right now, and that is the future.
Yeah.
So it's all out there for you. We've only gotten so far.
Thanks for the great talk.
You're welcome.
Right, anybody else? Any more questions?
I have a question.
Yeah.
Hi, Pedro. How are you doing?
Good. How are you?
Excellent.
Very interesting talk. These are really interesting concepts. I'm just trying to wrap my head around that concept of megacontinent. And what triggered my question is that you mentioned Eurasia as an example of the next megacontinent. So I'm just trying to figure out how do we put boundaries, because this is a continuum, right? And if I understand the point correctly, is that these megacontinents are a precursor of the supercontinent. But in the context of the continental masses that are existing at present, I would say that Eurasia is about, what, 50% of the whole continental masses. So is there going to be a gray boundary where we're going to be calling things megacontinents or not? What is your take on this?
Yeah, I mean, basically, the supercontinent cycle is probably a pretty poor term because it's not really that cyclic, and things things are breaking up in one place as they're amalgamating in others. So there's a continuum, and so it's really whether there's an accent on more amalgamation than breakup. So it's if you're in mineralogical terms, we're not albite, we're not anorthite, we're somewhere in between. We're oligoclase and andesine, and
right.
So, but the thing that's attractive about Eurasia is not size so much, is that it is amalgamated along the girdle, and the girdle that's bisecting the two upwellings. So this is just an example of a different perspective you get by bringing geology into the mantle convection framework. So if we accept we've got degree 2 planform convection, and we've got two upwellings bisected by a downwelling. Here is our most recent major continental collision event. Bang, it's right on the girdle. And the polar rotation that's responsible for that is about 90 degrees away from the collision zone. So it's exactly what you sort of expect. So that to me is more of a geodynamic driver than worrying so much about sizes and the sort of bookkeeping of whether things are coming together or not. It's just the fact that we get a new insight by looking at it in terms of mantle convection patterns.
Yeah, I think I get your point.
Am I rigorous about it? Absolutely not. It's just an idea, and it may not work.
No, but I think I get your point. It's better to understand this in terms of the time sequence, that this is happening before, instead of trying to figure out what is the mass that's going to make a critical mass.
Yeah, exactly.
Yeah.
Exactly.
No, great point. Thanks.
Right. Is there any more questions? Well, if not, we thank Dr. Murphy. Thank you, Brandon, and And hopefully we see you all guys in our graduate student symposium next week, Thursdays and Fridays. We're going to have lots of graduate students talk, so don't forget about that. Thank you, Brandon.
Thank you all very much. I'm glad you're not completely all zoomed out.
They're all in here. Perfect. Thanks.